Yeah, so hi everyone, I'm Omar. Today I will talk about open source. I will give a high-level introduction to the Hugging Face ecosystem and a bit to the open source ecosystem in general. So just as a quick introduction for myself, I'm the Chief Lab Officer at Hugging Face. I work in the intersection of open source, product, research, and technical communities. My main goal is to lower the barrier of entry for machine learning and making researchers' work as accessible as possible for more people to be able to adopt and use the open tools out there and the research that you are working on. Previously, I was at Google as a software engineer and a couple of other things. But yeah, let me just show an example of 2 years ago. There was this model called DALL-E Mini that was a text-to-image model. So you could write some text. So Moai statue giving a TED talk or Will Smith eating spaghetti, and it would generate these images. As you can probably notice, the quality of the images is not great, and this model again is from 2 years ago. And since then, we have gone a very long way. So just 3 weeks ago, Stable Diffusion 3 came out. Stable Diffusion is a state-of-the-art open model that can generate images. So these images that you see here, of course, are generated. So llamas visiting London, or an astronaut riding a green horse with a baguette. These are fully generated images. So it's quite impressive and quite inspiring how fast things are moving. And this is, of course, an example in the image space, but the LLM space has been quite similar. At the center of quite a bit of this is Hugging Face. So Hugging Face is an open platform that enables collaborative machine learning. Within Hugging Face, you can find many models, many data sets, and many demos. So those are the 3 pillars at Hugging Face. So right now you can find over 700,000 public models. Actually, probably even a bit more. Yesterday I was looking at some metrics, and today we are having in average 5,000 new repositories every day, which is quite impressive from the ecosystem. And just as you can find models, you can also go and find data sets, and you can find demos to try out the models directly in your browser. You can filter by task. So if you want to find a model to do text classification, or if you want to do speech recognition in Spanish, or if you want to do image generation, you can find the right model for your own use case. Apart from that, Hugging Face also does quite a bit of open source. So it's not just a platform, but also there are many open source libraries. You maybe already know about transformers. So there's transformers, there's data sets, and there are a couple of other libraries I will talk about. But before diving into that, I would like to give a bit of a background about why it's important to do machine learning in a more collaborative way rather than competitive and closed. So the first thing that starts to happen when ML is not collaborative is that the progress is very slow. You have many people reinventing the wheel. You have many different research labs doing exactly the same line or path of research. You begin to see people training exactly the same models. So for example, when the original BERT model came out, that's a very famous transformer model from years ago by Google. What started to happen is that different research labs started to train the model again and again and again, exactly the same model, the same architecture, and it was just reinventing the wheel. It was a bit of a waste of resources, both in compute and also in human time, right? So that's one of the points. The second one is that you alienate the community. What do I mean with this? So the moment you start to do all of the research in a closed source way, even if you do very interesting stuff, you're in some way distanciating yourself from the ecosystem. You work a bit as a black box, and the people will not be able to really understand what your model can fully do. And then from a business perspective, it's very challenging because then you have 20 companies racing to get the best closed source LLM rather than collaborate, and it's a bit of a race to the bottom. It becomes quite expensive at huge scale. So what happens once you start to do things in a more collaborative way? You begin to see people building on top of each other's work. You start to see people doing research in a collaborative way. Currently, there's a lot of stuff going on in Discord server, in Reddit, in many different public places. which really has accelerated the field significantly in the last couple of years. And from a business perspective, it opens new market opportunities. It's not now a race to the bottom, but more of a how can I use the model for an interesting use case. So usually, and you probably know about this, but when you work in an ML project, the expectation is that you pick a data set, you pick a model, then you train a model, and finally you deploy. The truth is that it's actually quite more nuanced. So it's a bit of a silly video, but currently, like if you want to do a project, usually it involves lots of experimentation, lots of different tools. It involves getting lots of hardware as well. Yeah, so in real world, building ML projects is not as easy nowadays, especially when it is about deploying models. Okay, so within this, Hugging Face has built a big group of open source tools that anyone can go and download. So all of this, of course, is free. As I mentioned before, transformers and datasets are some of the most well-known libraries, but there are many others. So for example, something that many people don't know if you're using PyTorch is that the default format that is being used, which are bins, allow people to run arbitrary code, which can be quite unsafe. That means that when you run a PyTorch model, you are potentially running any code. And safe tensors is a format that aims to be safe and doesn't allow people to run arbitrary code. People that are working in diffusion models, there is a diffusers library, people doing RLHF, which I will talk a bit more about in a couple of minutes, can use TRL. People that want to run models directly in the browser can use transformers CSS. So there's quite a bit of work that we are doing on Hugging Face side on building tools to make it more accessible for people to use models. So let me talk a bit more about models. And just as a brief story, so about 7 years ago, there was this famous paper called "Attention is All You Need," and this was really a pivotal moment in the NLP space because this was a paper from which all of the transformer research of the last couple of years spawned. And pretty much all of the researcher names that you see here, so all of the paper authors, went on to become very prominent researchers or created their own companies. So Cohere, for example, there's a bunch of interesting companies that came out of this group. And things have moved very, very, very fast. So there's this image I have from a couple of years ago, so from 3 years ago. And here you can see some of the popular or well-known open model architectures from a few years ago. So GPT, Roberta, T5, Electra, GPT-3 is not open source, but it has really moved very, very fast. So this is a bit more up to date. It's also 1 year old, but this is a timeline of models. I don't know if it's clear in your screen, but the model names that have a yellowish background, those are open models, and the rest are closed source models. And you can see that it's not just one company doing it. There is Llama by Meta, or Gemma or Flantify by Google, but really the number of groups that are contributing to the open ML space has increased significantly in the last year. So it's a very exciting time. And why is this research in transformers interesting? I think you already talked a bit in the last couple of days maybe about transformers, but just to give a very high-level view, the main idea is that you can do transfer learning, and that's why they are so popular. So in the classical ML setup, what you do is that you pick a data set, you train a model, that's it. If you want to solve a new task or a new domain, you will pick a new data set, pick a new model, train that new model, and that's it, right? In transfer learning, the idea is a bit different. The idea is that you can train a very large model, and then you can adjust that model for your own use case, right? So if you have done computer vision before, CNNs have been doing that for many, many, many years. Pretty much the idea with CNNs is that they work as a feature extractor, so they can identify which parts of the image are interesting. Then you can, so let's say that you have a very large model that costs millions of dollars to train, to identify, to classify images between 1,000 different tasks. The classification part is usually just the last layer. So what you can do is remove the last layer, add a new head, and then you can just adjust that with a new data set, right? So let's say that you want to classify if a picture has a llama or doesn't have a llama, and let's assume that llama was not a class in the original for the original model. Then with your own data set, you can use already this existing knowledge of the huge model for this new task. So that's what has been done already for computer vision for CNNs for many years. In the NLP space, it's a bit different, but the concept is the same. So let's say that I scrape the web for all English and Chinese text I find. Then I train a huge model. That model might be billions of parameters. It's really, really huge. It will cost a lot of money to train, most likely, because I need to get the data. I need to train the models. That needs compute, that needs expertise. But what is interesting is that this model will have, in some sense, a statistical understanding of text. It will be able to generate the next token. And thanks to all of this existing knowledge it has about language, you can now adjust the model for your own use case, right? So if you now want to train the model to be a sentiment classifier for English, it will be quite easy, right? You don't need that much data anymore. You don't need a huge data set. You can use the same model, add a new layer, so a new head, and then with the data set, you can just adjust this a bit, right? It's much better. This is maybe a bit clearer here. So what you can do is, for a base model with lots of data, lots of compute, and days of training, you get a pre-trained language model. And then, so that's something that probably just research labs with lots of compute resources can do. But then once there's an existing high-quality pre-trained model, you can fine-tune this model. You can train this model in your own laptop even, and it requires very little data, very little compute, and it's very easy to reproduce. And then you have a fine-tuned language model. And this end task can be many different things. It can be, let's make this model a conversational. So let's have conversations with the model. It can be to do translations. It can be to do a bunch of different tasks. So originally, transformers were just for NLP. That's where they shined and where they became popular. But recently, they are being used more and more in other domains. So in audio, in speech, so for example, to do speech recognition, to do different computer vision tasks, and in a bit more exploratory sense, they are starting to be used for time series, biochemistry, action decision, for robotics, and a couple of different things. So there is this state of AI report. It's done every year by a group. It's an open document that anyone can check, and they were predicting that transformers will expand beyond NLP. So that was in 2020. And this is a graph from 2022 papers. And you can see that, of course, transformers is being used not just for text anymore, but also for image, multimodality, audio, video. And again, this is from 2 years ago. This was before Sora, Open Sora, all of this multimodal work happening with a bunch of different models recently. So this has definitely increased even more since then. So we talked that people can go big models, large pre-trained models, and then fine-tune for their own use cases. So then people can go to Hugging Face, and on Hugging Face you can find pre-trained models. So you can find Llama or Gemma or BERT-based. But people can also go and share their own fine-tuned models, right? So if you fine-tune BERT to do text classification, certain tasks, you can go and share the fine-tuned version there. I like this screenshot because it's a bit old. It's from a presentation I did almost two years ago, 2.5 years ago. So back then, there were only 14,000 open models. Nowadays, there are over 700,000 models. And it's quite impressive to see how much the community is really sharing. So yeah, just to reinforce a bit, usually you go to the model hub, you pick a pre-trained model, you pick a data set that might be on Hugging Face, or it might be a data set on your own computer or your own server, and then you will fine-tune the model. And usually what people do is that they share it back to the community. Going a bit more to the open source side of things, so there's the Transformers library. The Transformers library, again, is an open source library that supports many of the popular transformer architectures. So it has support for Gemma or Llama, for example, for Qwen as well. And you can go and with very few lines of code and with a very consistent API, no matter what the model is under the hood, you can just load different models. So if you want to use GPT-2 and then you want to switch to Qwen and then you want to switch to T5, it's usually just changing the ID, the name of the model here, but otherwise the whole code should work well. And Transformers is quite powerful because it really abstracts quite a bit of the implementation details, but it also helps you train models. So this is just an inference example, but here pretty much what we're doing is we load the model, then we load the corresponding tokenizer. We tokenize the text, and we specify that we want PyTorch tensors being returned. And finally, you just do model.generate, which will take care of generating the next token IDs, right? And finally, you can just use the tokenizer to decode back to text. So here you can see a very simple example using GPT-2 large to generate a very simple string. And I know that this sounds kind of obvious nowadays, but this was not obvious at all, or it wasn't easy at all a few years ago. So it's quite nice that the barrier of entry to start using these models, even if you don't know too much about machine learning, is much lower nowadays. To share an example from the community, there is a project called Big Code. So if you're familiar with Copilot or with other tools that take care of generating code for you, the goal of Big Code was to do an open source implementation, an open source replication of Copilot. So, of course, as always, the center of this kind of efforts is usually the dataset. So this effort released a dataset called the stack. The stack contains billions of code-related tokens. So it has Python code, JavaScript. I think they have 300-something programming languages. And all of this is permissibly licensed code. So this is code that, so they went through software heritage and GitHub. They went through code, but they respected the licenses of all of these code bases. Once the dataset was released, the community did different things. So first of all, you had companies pre-training the model for different for different things, but with this dataset. So people from Stability trained stable code, from Salesforce did CodeGen, from Replit they did Replit code, and Desi did Desi-Coder. People from the open community also started to do their own fine-tuning. So at the left, you have community pre-training. So that's people that are pre-training a very large model from scratch. You also have people that did fine-tuning. So within the Big Code effort, they also release a couple of models. So they released Struct-Coder Base, for example, and then people from the Wizard group, from Bangu, from Debug, they also fine-tuned Struct-Coder Base with their own data sets for their own different applications. So it's quite interesting to see how from just a data set, you can have this whole ecosystem growing around it. It really makes the research of the original researchers of the stack much more impactful than what it would have been if they just released a model as a single artifact. And the community has grown a lot. It's really, really, really huge. So Meta, for example, has released Llama 2, Llama 3, CodeLlama. Stability has been doing stable diffusion models. OpenAI has done Whisper and Clip. These are a bit old, but not that much, really. There is Big Code, as I just mentioned, and there is Mistral from France that has been quite popular with Mistral 7Bs as the base model, but then the community started to do Zephyr, OpenChat, Novus Hermes, and other models around it. So it's quite empowering. And just as an example, last year Mistral released, no, actually this year, this is from April 10th, Mistral released the mixture of expert, A times 22B model, and they just did a tweet with a magnet link to download via a torrent, because that's the way they like to do the releases. And in just a couple of hours, 6 hours, the weights were converted to the Hugging Face format, and they were shared with the community on the hub. And it's quite impressive because this is a 140 billion parameter model that was in 6 hours converted and uploaded, and people were already having access to use it. It really lowers the barrier of entry to using it. And just 2 days later, there was a model called Zephyr, which was the state-of-the-art, the best state-of-the-art open model back then. So this was a conversational model. And yeah, people did experiments, research experiments of very high quality in just 2 days. So that's another example of how doing open research and open work can make things much more impactful. So we talked a bit about models. Let me just switch gears a bit to talk more about training and inference. And I think Tom will give a much more detailed talk about this. So some of these might have a bit of overlap. So I will try to be very high level on this part of the presentation. So usually, as I mentioned before, you do 3 things, or 2 things, sorry. You begin with the pre-training, and the pre-training requires lots of data, finding the right ways to train at scale, and then finding how to evaluate these models properly. The second part is usually fine-tuning, and within fine-tuning, we have the traditional fine-tuning, and then we have RLHF, and I will talk a bit more about this. And finally, there is how to deploy these models and how to run this in consumer GPUs. So let's talk a bit more about training, but pretty much the assumption is that if you train with lots of high-quality data, a model will be good. That's kind of the main assumption under most of the LLM research in the last couple of years. So if you look at the transformer architecture from 5 years ago versus now, the architecture is almost the same. There have been a couple of very minor changes, but most of the changes have been in either the data, so improving the quality of the data, or changing how the model is trained. So you don't change that much the model architecture. You just keep scaling it up, keep scaling up the data, and improving the quality of the data. And that tends to give good enough results. Where to pick this data? Again, Tom will talk a bit more in depth about this, but what people usually do is that they go to Common Crawl, which is a crawl of all of the web, and everyone uses this. This has few hundreds billions of tokens. If you want to use code, people use GitHub or Software Heritage. Software Heritage is an organization that preserves code, so they have very huge code bases. And then if you want higher quality data, because of course Common Crawl contains low quality data. It contains data from Reddit and from platforms that might be toxic. So for curated data, there is Wikipedia, there is the books family of data sets. So there are open domain books that you can pick. There is FindWeb. FindWeb is a very recent project that was released just a couple of weeks ago. They contain 15 trillion tokens, which is a lot. And just loading this requires 44 terabytes of this space. So it's a high quality data. There is this blog post that you can check. It goes into extreme detail into how this data set was created. And they also did FindWeb Edu, which is the educational slice of this data set. So usually from a couple of papers from the last few months, the results seem to be that if you train a model with educational data, the quality of the model will be in general much better than if you just train with all of the data. And there is a recent trend called synthetic data. So that's just generating data with another LLM. So you might have a very high quality LLM of 100 billion parameters. You can use it to generate synthetic data, and then you can train a very small model with this synthetic data. This is a bit more experimental or in early stages, I would say, but it's quite interesting. And this is just a screenshot of the FindWeb pipeline, so how they retrieve the data. And it's usually extracting millions of URLs, then extracting the text, filtering for the languages that you care about. There are different deduplication techniques to make it, and also removing PII, so any private information such as phone numbers, emails, all that kind of stuff you usually need to remove as well. Of course, with the rise of very large models, you also start to face challenges. So, for example, the models are so large that they might not fit the computer. Evaluating the models is not something that is very simple. Optimizing the model for your own use case is not trivial. And finally, optimizing for them to run very quickly. Again, that's another of the challenges. So just to give you an idea of why a model is large, when we talk about a model, we usually talk about a number of parameters. So for example, let's say that you are working with a 40 billion parameters model, then you might have the question of how much GPU you need to load this model, right? And there are just two variables that matter for being able to load the model. So one is just how many parameters the model has, 40 billion. And finally, the precision. So precision is how many bits you need for each parameter, right? So for example, if you use FP32, which is how people train models, that's usually 32 bits per parameter or 4 bytes. And that means that if you will need a GPU of 160 gigabytes at least just to be able to load the model. This is not to train the model. This is just to be able to run the model in your own computer. So what most people do usually is run the model in a lower precision. So for example, you can do a float point precision, so FP16 or BF16. That means that you require just 2 bytes per parameter, and that reduces the number of gigabytes that you need to load the model. Of course, quality begins to degrade as you go lower and lower, right? Because you start to have less information in the network. There's quite a bit of research into this. So up to FP16, models work well. So you can cut the precision by half. That's not an issue at all. You can usually go down to 8 bits. So you can go to 1 byte per parameter. And that still works quite well. Not always, but most of the time. And there's lots of work right now going into very low ranges. So 1 bit per parameter. For a mixture of experts, people are exploring sub 1 bit per parameter, that kind of stuff. Yeah, so this is just to give you an idea. So as you go lower and lower, you require less gigabytes to load a model. And then there's this question if can we leverage this also for training? So when we talk about pre-training, you require lots of money, lots of data, lots of expertise. When you use fine-tuning, you require less compute and less data, which is great. But now that the models are so large, so for example, let's say that you want to fine-tune a 4TB model. I don't know about you, but I don't have a 80 gigabyte GPU in my computer. So people started to do PEFT. So PEFT is a family of parameter-efficient fine-tuning techniques. They allow you to fine-tune a model using even less compute. So the main idea of PEFT is that you can fine-tune a pre-trained model on a task without modifying most of the parameters. So when you do fine-tuning in the traditional sense, you will adjust all of the parameters of a model. The main idea of PEFT is that you can freeze the main transformer model. You will add a small, very, very small auxiliary network on the side. And when you fine-tune the model, you will just adapt the weights of the auxiliary network while the main model is frozen. So here, maybe it's a bit clearer in a more visual way. So this is LoRa, which is one of the PEFT techniques. So here at the left, you have the original pre-trained model. This is frozen. Here at the right, you have 2 small adapter networks. I won't dive into why there are 2, but you have 2 very small adapter networks. And when you fine-tune the model, you are just modifying the orange. And again, these are networks that are very, very, very small in comparison to the original model. That means that when you do the training, you don't need to be modifying these weights, which really reduces the amount of GPU you need. Something that is also interesting is that after doing the fine-tuning, you can merge these networks, the auxiliary networks, back to the original model. So at the end, you will have a model that is exactly the same size. So it does not increase the size of the model at the end. The model will be just as fast as it was before. And yeah, it will give you almost as good results as if you did a normal fine-tuning. On the con side, though, the training will be a bit slower because you need to do additional operations on here. LoRa is just one of many techniques. LoRa is probably the most popular technique to do PEFT nowadays. So if you haven't done it, I definitely suggest you to explore this a bit. So for example, if you have a 10 gigabyte GPU, which most people with a consumer GPU have, you can fine-tune a 7B model, such as Mistral 7B, in your own computers, or even in free Google Colab, or in many of the free different resources to do this. This is not just limited to text. You can also do this with diffusion models. So, for example, you can use adapters to learn different concepts, right? So you can use an adapter to learn the concept of a dog, an adapter to learn the concept of a toy. You can merge the adapters together, and then you can merge concepts. So you can have an adapter that does both a toy and a dog. Okay, so we were able to do the fine-tuning using this compute, but now there's the topic of alignment. So when you have used one of the many models out there, you have probably faced a situation in which the model declines to answer about a topic. So this is an example from Cloud, from Anthropic, in which the user asked, how can I kill all my Python processes in my computer? And the model says, sorry, but I cannot give you recommendations about how to harm a process or a system, right? So this is, of course, a very aggressive denial of a reply. So a model saying that, hey, I cannot help you with the homework, or sorry, but as a model, I cannot give an opinion about politics or something like this. And you have probably noticed that different models have different behaviors. And this is not something that is done in the pre-training. The pre-training is done exactly the same. This is actually done in a post-training stage called alignment. And alignment, and again, Tom will talk a bit more in depth on this later. But alignment is a way to make a model behave in some way, right? So you might want your model to be extremely helpful and to reply any question that the user might ask, or you might want your model to be extremely harmless. And if the user asks, hey, how can I build a bomb? Or how can I explode something? You will want your model to decline. It depends on the model creators, how this is implemented, and which are kind of the values of the model. And the way to do this is doing RLHF, reinforcement learning with human feedback. Last year, it was not easy. Last year, it required using a reward model, reward functions, having a somewhat strong reinforcement learning skill set. Since then, it has become quite easier. But just to reinforce a bit more, so when you pre-train a model, you have a model that will just generate the next token, right? It will not be a conversational model. So if you are expecting a model like ChatGPT in which you can talk and the model will give you like a conversation, like answers, a base model will not work very well for that. That's why you need to do alignment as well to make sure that the model will be conversational enough. Since last year, there has been quite a bit of research in the RLHF space. So there's IPO, KTO, DPO. These are techniques that remove the need for a reward model. They are very easy to implement. They don't require too much compute. And they are very nice open implementations of this. There is a library called TRL, that's by Hugging Face. It's an open source library that allows you to do RLHF, including these techniques. Something that we have been doing at Hugging Face is doing alignment handbook. So it's a series of recipes on how to do RLHF and alignment for popular use cases. So Zephyr was a project we released last year, and with it we released a toolkit for people to be able to very easily, just writing a script, replicate exactly the same model. So the data is open, the model is open, the scripts are open. Here is an example using TRL. So pretty much what we're doing on the snippet at the left is that, we load a data set, right? So we load the IMDb data set. So that's using the datasets library. We load a model. So we're loading Facebook's OPT model with the transformers library. And then TRL offers some very nice wrappers called SFT trainer, for example, that allows you to just pass a model, pass a dataset, tail, which is a column that has text, and then trainer.train, and then the model will take care of the training. So TRL includes PEF techniques. So it includes LoRa and quantized LoRa. It allows you to fine-tune on consumer hardware, and it has some of the state-of-the-art algorithms. So supervised fine-tuning, it has DPO, it has KTO. And this is, of course, a very simplified example, but the documentation is quite complete into everything you can do with it. So finally, we were able to train models, we were able to do fine-tuning, we were able to do alignment. The next question is how to run these models, right? And as I already hinted before, you can use quantization to load the model using the bits. There are many different libraries for this. There's one called Bits and Bytes, which is quite popular in the ecosystem, and it has support for ways to load models using 4 bits or 8 bits per parameter. We are also starting to enter the world in which there will be models that will not fit in any GPU, right? So there are models that might be hundreds of billions of parameters. And in those cases, what you will need to do is distribute the model across GPUs. There are libraries such as Accelerate that allows you to do that. And it's not something that you need to think too much about in general, but if you start to work with models that are very, 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 very large, you will need to start thinking about this as well. And finally, running inference for these models is not trivial. There is quite a bit of research on how to do inference as fast as possible. And there are open source libraries and tools such as TGI and BLLM that allow you to do inference in an optimized setup. Okay, so finally, we were able to train the model. We were able to run inference, and you might think that you are done. As a researcher, sometimes we train a model, we think that we're done, and we go to the next research. But usually what happens next is that you will want to put the model in the hands of the people. So at the beginning, I was showing screenshots such as this, minions eating tacos, or the Demogorgon from Stranger Things holding a basketball. So interfaces in which people can write something and then generate images, or in the case of LLMs, imagine ChatGPT, or interfaces in which you can write some text and then generate some images, right? So these are demos, and although they sound trivial, they are quite important in a release process. Deploying a demo is not trivial. It's not as easy as it would sound. And in general, ML people are very scared of web technologies, so people don't like to do HTML, JavaScript, that kind of stuff. And why are demos interesting? So first of all, demos really allow you to get a much more diverse audience trying out the model, right? So if you just have ML people trying out a model, you will not find edge cases that if you have a very diverse audience, they will find. As an example, we work quite a bit with people in the healthcare ecosystem. We work with doctors, and actually being able to build this kind of demos and putting them in front of the doctors have allowed us to make it easier for doctors to understand what are the capabilities of the model. If you have read papers, you have probably seen results that are somewhat cherry-picked, so they look very nice, but they are not really reproducible. Demos are nice because then you can go try out exactly the same input and see if the model, how the model works, right? So when people release a new LLM, setting up a demo can really make a huge difference, because that really allows people to try out the model and see how well it works. In comparison, if you don't release a demo, people will need to download the model, learn how to run inference with the model, find the right setup for their own hardware, right? And that's much harder, and that's not very friendly for non-ML people. So in the traditional world of setting demos, you have to train the model with your tools, then build a container with Docker, for example, then see how to store examples, and finally build an interface with HTML, JavaScript, CSS. Nowadays, and all of this, of course, work with different languages, so Python, Bash, SQL, HTML, JavaScript, CSS. Since then, we have gone a long way. So there are open tools such as Gradio or Streamlit that allow you to do all of this entirely in Python. And here is an extremely minimal Gradio example. So Gradio has three components. So you have an input. So for example, here the input is an image, right? You have an output. So an output can be an image, it can be text, it can be whatever. So here you just specify which is the type of input and which is the type of output. And Gradio has support for many modalities. So you can have an audio, you can have many different things. The third part is classify image, or here is whatever Python code that you have to run inference. So this can be any Python code. If you use scikit-learn, it can be scikit-learn. If you have a weird research code base, you can use the weird research code base. So, but here is just a function that takes as input an image and outputs a label. And this you can run pretty much anywhere. You can run locally in the Bash terminal. You can run in Jupyter Notebook. You can use in Google Colab. So you can run this in any environment that you have. And it's quite easy to set up. But of course, you cannot share a Google Colab with people. I mean, you can, but people that are not technical will struggle with it. So that's where Spaces fits in. So Spaces is the third pillar of Hugging Face. It's a platform where people can go and find open source demos of open models. People can also find things such as leaderboards. So if you know the LMC's chatbot are in a leaderboard, or if you know the LLM leaderboard, they are also hosted on Hugging Face Spaces. And here, for example, is an example of Quen. So you can just type, how do I get a llama out of my backyard? And then the model will give you the output. And you are doing this entirely in the browser without having to set up anything yourself. Of course, the Quen authors released the demo. But yeah, the idea is that you can make your work much more reproducible and open and accessible if you build this kind of interactive demos for people to try out. And again, I talked mostly about Gradio, but if you want to use Streamlit, if you want to use Docker, if you want to use just static HTML, you can use that. You're not constrained to our tools. And it's quite exciting because the ML ecosystem has changed quite a bit. Until a few years ago, only ML people could use the models. Now, software engineers could use the model, but now with things such as Spaces, if you have a web browser, you can go and try out the model. When DALL-E Mini, the model that I showed at the beginning of the presentation, came out 2 years ago, people were, the demo went viral. People were in TikTok and in social media sharing images generated with the model. And again, these were not technical people. So it's really a way to get a much wider audience to try out the models. And yeah, the AI ecosystem has grown a lot. There are many, many, many different tools out there. So from Llama CPP, TensorFlow, Keras, Hugging Face, Nose Research, there are many open Discord servers that anyone can join and start contributing to research efforts. I think it can be a bit overwhelming because there's too much happening nowadays, but it's also a great moment with many areas of opportunity. Yeah, I think it's a very exciting moment in the open space. Thanks.